Hi, I'm Philip. I do research at CyberReason, and this is abusing WMI providers for persistence. Now, what every attacker wants after doing all of the cool stuff like code execution and privilege escalation is persistence, or to be able to run your calculators after the machine restarts. Of course, you could substitute calculator with some useful payload, but still, you want to run after the machine restarts. One such common technique, at least nowadays for persistence, is COM hijacking. Now, COM, or the component object model, is just another way to interact with external code. You basically say, I want to interact, use this external piece of code identifiable by a class ID, which is just a GUID-like identifier, and you tell the OS, oh, I want that object. And the OS knows how to retrieve it, load it, and then you can interact with this outside code. Now, behind the scenes, this is implemented by the registry. Each such class ID has its own separate registry key, which contains a couple of subkeys that have the implementation of that COM object. So if it's a DLL, it just gets loaded into your process. If it's an executable, it gets loaded as a separate process, and then you can communicate with it. But all in all, you just ask the OS for a specific class ID. It loads it, and you can interact with it. Now, abusing this is pretty straightforward. Like pretty much every kind of persistence, it's a combination of registration and demand. You try to find which COM objects are requested at boot by Windows, and you just become that object. You can simply modify the registry, the class ID entry of whatever object you want to hijack, and instead of the original object, instead of the original implementation executable, you just write whatever you want. Basically, whether it's your DLL or it's some kind of command, etc. Now, this is pretty popular in recent times, but there are a couple of problems with this technique. First of all, not every COM object is requested at boot, so you have a limited number of objects you can hijack. And also, to do this, you need to modify existing COM objects, which is a thing that doesn't really happen legitimately. So it's a pretty rare occasion, and registry could be monitored pretty easily. Now, you could, of course, create a new COM object, but there's nothing to demand it. So you just basically have a registry entry that does nothing unless you write some other piece of code that demands it at boot. But then this kind of defeats the purpose, because now you have to persist this new piece of code. So the question I asked myself, which was also the basis of this research, is there any feature of Windows I could just coerce into loading any arbitrary COM object? And it turns out such a feature is WMI. Now, WMI is a feature of Windows that provides an object-oriented representation of lots of unrelated elements on a machine. This means there are WMI class representations of processes, services, but also of hardware components such as monitors and network adapters. And I can just ask Windows to enumerate some WMI class, such as Win32 process, which represents the process. WMI enumerates whatever this object represents and gives me back all of the instances of this class. Here we can see it just gives you something pretty similar to a task list. Now, behind the scenes, WMI providers are the pieces of code that provide this kind of magic. There are a couple of COM objects, exes and DLLs, which implement the actual enumeration methods into instances and classes that comprise WMI. Now, these WMI providers are only loaded when something requests a relevant WMI class. So if I have a provider that implements Win32 process, it isn't loaded until I ask for Win32 process. Now, all of these providers and the classes themselves are defined in what's called the WMI repository, which is just a couple of files on disk. The providers themselves are also defined as WMI classes, specifically as the _Win32 provider. Now, this is a pretty big object, but we actually have only two interesting fields for our purposes. First is a name, because we need to refer to it somehow, and second is a class ID. Now, the class ID is exactly the same class ID as in COM. Each WMI provider could be implemented as a COM object, and we could just, if we're an admin, and I'm assuming I'm an admin because I play in easy mode, I could just create my own WMI provider and provide it with an arbitrary class ID. Now, this means each time the provider loads, my COM object loads. But again, nothing demands this WMI provider. There are no classes that are requested at boot. So let's look at what WMI providers actually exist when the machine boots. So actually, there's quite a few such providers, one of which is WMI Perf Inst. The others sometimes change between machines, between laptops and desktops, etc. But WMI Perf Inst is one such provider. Now, when something demands a WMI provider, it actually demands a WMI class. And it, in turn, demands the COM object. This means we have two new levels of indirection with which we could play until we somehow achieve execution at boot. Now, let's look at how the association between a WMI class and a WMI provider works. It turns out that if we look at a class that's implemented by this WMI Perf Inst provider, we can see that the provider is denoted as part of the class itself, and it's identified by name only. This means it's just a string. So the way we could abuse this is pretty simple. We find an instance provider that's loaded at boot. Here it's WMI Perf Inst. We just delete it. And as an admin, we could register our own WMI provider with an arbitrary COM object as an implementation and give it the same name. So if a class is requested at boot, WMI looks for the provider with the name which corresponds to the implementation and loads that. So this means we've achieved something that looks like COM hijacking, but we didn't really hijack any COM objects. And if you're not looking at WMI, at specific WMI events, you're going to miss what's happening. Now, it's pretty easy to implement, and if you have a COM object ready, it's about 6 lines of PowerShell. You simply delete an existing WMI provider, create your own, and that's it. But still, hijacking is pretty invasive. And when you hijack some kind of object that is used by the operating system, you need to somehow proxy to the original object or re-implement some of its functionality, or just hope really hard that nobody notices that something's not working. Well, in fact, COM hijacking really sometimes depends on people not noticing stuff isn't working, because there's a lot of COM objects loaded at boot which do pretty much nothing important. But still, can we avoid hijacking? Because that would be much, much easier. And it turns out WMI still has the answer. And it's in WMI Event Providers. Now, WMI provides an eventing functionality. This means there are special WMI classes which act as events. You can subscribe to a type of event, and each time this event happens, you could have some kind of callback, consume this event, and run your own code. Now, there is an infamous persistent technique which uses the consumption of WMI events, this is something a bit different. And we're going to use the event providers themselves. Now, it turns out the association between event classes and event providers is done a tiny bit differently, which works in our favor. Instead of having a specific WMI class that tells you, here's my implementation of the provider, there's a separate class called _event provider registration. The way it looks is it creates an association between a WMI provider and some kind of WMI query which describes the scope of events this provider could provide. So let's say I want to get all MSFT SCM events. This means the SCM event provider is going to be loaded. Now, the nice thing about that is WMI event providers also allow for redundancy. So multiple providers could provide the same events. This means I could register an additional provider to provide an event that's already provided to WMI. Now, of course, we need to check, is there any demand for any WMI events at boot? Because again, no demand, no execution. And it turns out that on every machine I've checked, at least one of the events demanded is the MSFT SCM event, or SCM event log event, which is provided by the SCM event provider. So now we have a pretty simple way to piggyback on that same demand. What we need to do is create, again, our own WMI provider, provide it with our own COM object, again, unrelated to any other COM objects on the machine. This means it will probably be overlooked because COM objects are created pretty much constantly because lots of installers and stuff like that create their own COM objects, so this really isn't uncommon. And we could register it to provide MSFT SCM event. And what happens next is at boot, the machine tries to consume SCM events. It loads the original provider. It looks, is there any provider that provides these, is there any additional providers to provide this event? The answer is yes, our malicious provider. And that's how we persist. And this is also really easy. The only thing we need to do is create a new provider, create this event provider registration. We do not delete anything. We do not override anything. And we achieve persistence with an arbitrary COM object. And if you're not looking at WMI events and WMI providers in depth, there's pretty much nothing you can do to detect this unless you detect the payload itself. And that's about it. So 1 minute is enough for questions, but you could ask me outside or something. Thank you.